All right, hello and welcome to our Skew The Script speaker session with the researchers from UChicago, Julia Koschinsky and Nikhil Patel, who helped create our new 4.2 random sampling methods activity, allowing multiple cities across the country to actually sample incomes representatively from their own cities, whereas before it was only San Antonio. Both Julia and Nikhil come from the Center for Spatial Data Science at the University of Chicago, which focuses on the spatial angle of data and analyzing data in spatial terms. And it's a field that often goes understudied and is one that I think UChicago is really leading in. And we're just so lucky to have them. Julia is the executive director of the center, and Nikhil is a student at UChicago who jumped in and helped on this project in a huge way. And so we're so thankful for them for donating their time and resources and intelligence to helping us expand this activity for classrooms across the country. So just to give everyone context who's here, I'm going to quickly screen share and show some of the new materials that we have, just so we're all on the same page. And then I'll turn it over to them to discuss where they're coming from, spatial data science in general, and how they made these incredible maps and what's next going forward. So I'm going to go ahead and share what the current maps look like on the site. So our old version of the activity just had the city of San Antonio, and it looked like this. And it was me creating it while I was teaching in my school in San Antonio, looking at census data for multiple years and doing some balancing of how to make these incomes representative of the city and different tracks in the census data. And it took a weekend. I just sat down in the San Antonio Public Library, banged it out, and the rest was history. And the question was, could we take that process of trying to balance demographics, incomes, summarize millions of data points into 100, and make it into an activity that pedagogically fits the needs of teaching random sampling methods? Could we do that not just for San Antonio and doing it manually, but automate it to do it for many cities across the country? So the result of that work is what you see now in the updated lesson 4.2. And in the updated lesson, we have a map for many cities across the United States. For example, I'll go ahead and pull up here Chicago, where our great speaker friends are joining from today. So here is the city of Chicago represented as 100 homes that are representative of the neighborhoods that they're in. The homes are sized by income and colored by race, ethnicity. And the goal for the activity is to try and figure out what's the median household income in this case, the city of Chicago, using the different sampling methods from our course. And one new thing for this new activity is that instead of having clustering by you pick a home, find 4 homes around it, or you stratify by race, ethnicity, we actually group everything by regions in the city. And by doing different sampling methods that group by those regions, we get to really see key differences between the sampling methods, which helps fits the pedagogy need of teaching these sampling methods for AP stats. And of course, as you sample through them, you create a sampling distribution of all your students' median estimates for the household incomes, and you get to discuss which might be biased. Why is there more error here? Why is there less precision? And you eventually end up getting a really nice handout key that shows you the trade-offs between using these different sampling methods in those same cities across the country, and shows you where students' samples are likely to fall relative to the true median income for the city. And in addition to the activity day, as before, there is a second day with post-activity notes in which students get to take that great exploration of different sampling methods, talk about the trade-offs between them, talk about bias versus error, talk about precision versus accuracy. We do have systematic random samples still in here, but in different contexts, and then have this really engaging discussion about school finance and how differences between income and neighborhoods can lead to differences in school funding, and what policy remedies, if any, should be done about it, and having that discussion in class in a multi-sided way. So that's a quick summary of the activity as it exists now. And as you can see, it's so greatly expanded to all these cities across the United States. And now I'm going to turn it over to our guests to share how they did this. and what it is they do with spatial data science to make things like this possible. And we're so lucky to have them with us. So I'll turn it over to Julia and Nikhil now. Thank you so much.
Great. Thank you so much, Dash. We've been really inspired by your work and by all the teachers in your network. So it's been a real joy to work with you on this. So let me go into full screen here. 1 second. Can you see this okay? Okay, so we'll quickly start by saying who we are. And Nikhil, since you're the MVP on this team, why don't you start?
Hi, everyone. I'm Nikhil Patel. I am a second-year undergraduate at the University of Chicago. Second-year undergraduate means I was also just a high school student at Libertyville High School in Libertyville, Illinois. So I feel like I brought a recently high school student perspective to making this lesson. I am studying, I'm not quite sure right now, but probably computer science and applied math.
Great. And then on the team as well, but not here today, is Nico Marcio. He's a research data scientist at the Mansueto Institute for Urban Innovation here at University of Chicago. And as Dash mentioned, I'm with the Center for Spatial Data Science. And I originally reached out to Skew The Script because I'm involved in a project to integrate scientific reasoning with spatial data science education. And as part of that, we have a workshop that involves high schoolers. And let me actually, in the chat here, include the links that I'll be talking about during the presentation. And in these initial 2 links in the intro, Mapping Africa is one of the projects that Nico has been working on to give you a sense of, what web mapping looks like. It's for Africa. And then this scientific reasoning project is putting science into data science. And the remaining links I'll get to, in my section. So we'll have time for your feedback and Q&A at the end, but if there's anything that we don't get to, or if you have questions after the webinar, this is the email, spatial@uchicago.edu, where you can reach us. And, for instance, if you wanted to discuss geographic information systems or high school teaching of spatial analysis in more detail, feel free to reach out to us afterwards. So what we wanted to talk about is first a little bit broader context of what spatial data science is, so that you have a sense beyond the particular lesson that we worked on, which Nikhil will cover and give you an under the hood perspective after my part of the presentation. We'll, as Dash mentioned, give you a quick preview of what we have in store for the future. And then the remainder of the hour will be Q&A and your feedback. And we'd love to hear about ways that we can improve the map as well. Let me just check in the chat. There's one message. Okay.
Oh, sorry, that was just me.
Okay. Sounds great. So, what is spatial data science? So spatial data science is a subfield of data science. And so then the question is, what is data science? So data science really emerged because there's more data available now than has ever been there before. And we need new ways to make sense of all this data. And so to do this, data science emerged to combine computer science methods and tools and statistics. And so spatial data science combines specialized spatial computational and statistical methods to generate insights from geospatial data. So where matters, right? Or let's say where is important, when location matters, then spatial data science is relevant. And I've been with this team for 20 years, and what happens when you hang out with, spatial data scientists for 20 years is you start to think spatially. And so that's why, Nikhil and I are wearing our center shirts, which are about, spatial thinking. So you start to think of everything in locational terms. I was talking to somebody who does brain research recently, and they have XY coordinates with an additional dimension. And so I'm thinking of that, in spatial terms in a bit more abstract way as well. So here's an example that Nikhil generated of what spatial data science can look like under the hood. So on the left, you see his code. In this case, it's R, but he also had an earlier implementation in Python. And that code generates the maps that are part of the lessons that Dash showed us before on the lower right. And so this code implements spatial packages on the computation side, as well as some spatial methods. Now, what do we get? What's the benefits from using spatial data science? I'll go through a couple, and also some drawbacks. One is automation, right? So Dash described how he created that one map. With code, we can automate that process and generate in one batch 100 maps now, right? The second is replication. So if you are from a city that isn't covered in the 100 that we created, and you wanted to add that, you could use the code, replicate the whole process, and then generate that for another location. Third is ease of use. So as I mentioned, we've been using R and initially Python, which are languages that are easier to use than some other programming languages. So for instance, Nikhil, when he started, he didn't know R, and then picked it up, as part of the project. Then updating is much easier. So if you give us feedback on anything that you want improved, and that those improvements are feasible, we can then update the maps and include those improvements without having to manually redraw 100 maps. Accountability. So the code is open, which means that you can trace how we got to the results that you see. And if there are any bugs, then anybody would be able to go and track those. Then on the drawback side, there's also a loss of human touch. So because this is now based on an algorithm, which gets us all these benefits, we're losing some nuance in terms of each city's peculiarities that you can take into account when you're manually drawing this. So we talked about spatial data science combining spatial, computational, and statistical methods in order to gain location-specific insights and from spatial data. And so I want to talk a little bit about, give you a sense of what spatial data types exist, because each of these data types come with their own specialized methods and tools. And so this is an example of area data that comes from the Million Neighborhoods project that I shared earlier that Nico developed. And so this is an example of mapping areas. Then mapping points. An example of that is the lesson that you looked at. And in that case, points are people. Points can also represent events like diseases or crime, or they can be measures from sensors, as the map on the right shows, where for instance, you have pollution monitoring stations that are then the values of that are interpolated to a surface. You can also map lines of flows. So in this case, we're looking at the historical development of petroline pipes in the US. And in the geophysical sciences, there's a lot of mapping of remote sensing images. For instance, here's an example of the classification of land cover. Then if you wanted to use spatial data in a classroom context, here's some examples that I also put in the chat. The top 3 are free and the other ones are subscription-based. And I'd be happy to go into detail on the Q&A. What do spatial tools and websites look like that you can use in a high school context? I'll go quickly through a few of these. One of the things that we've used, one of the tools we've used more extensively is Kepler, because it runs on Chromebooks and it's free, web-based, and useful for basic geovisualization. Then one of our own tools is a desktop-based program that's free called Geoda. The link is also in the chat. It's cross-platform and it's for the analysis of spatial area data. So it combines geovisualization with some basic statistical techniques. Then for kind of full-blown geographic information system or GIS, there's QGIS. That's a desktop application. And then the most well-known commercial GIS is called ArcGIS. And there's free educational licenses, I believe, for high schools as well. And then, as I mentioned earlier, there's specialized spatial packages in Python, like GeoPandas, and in R, and there's a whole website and book for spatial analysis in R that I'm linking to here. So next, here is an example of the Data for All high school workshop that I mentioned, where students are using Kepler. They had a 10-minute training on it and were then up and running, with some data here, in this case on cholera. And so it's, pretty easy if you only have Chromebooks and internet connection and not much time to get students up and running in this. So let me show you what this actually looks like in practice. So this is the Kepler interface. This was originally developed by the team, a team at Uber. So it has really good representation of flow data as well. And in this case, I'm loading the point data from the lesson for Chicago. And the colors are representing the racial categories. The size of the circles are representing income, just like in the lesson. The big difference here is that this is now part of an interactive map and has associated data with it. And so when you click on the data table, you get all the variables that are associated with each point and can then dynamically explore this. So for instance, here you can hover over each of the points and get the associated data that's underneath. You can zoom in, scroll around, look at other data points and their content. And then you can style and customize the look of the spatial data. So next, I will give you an example of Geoda, which combines geovisualization with some basic spatial statistical tools. And so here we're looking at, on the left top, a map of community areas in Chicago. And the data that you see is about incomes. The color coding works so that darker areas are higher incomes. And so you see a concentration of higher incomes in the northeast of Chicago. To the right of the map is a box plot that represents that same per capita income variable. And on the dots on the top represent the neighborhoods with the highest incomes. And so next, I'll be loading maps for the percent of 3 racial groups: whites, blacks, and Hispanics. And you can then see the distribution in comparison to income. So here we have percent white. So this matches the concentration of higher incomes in the Northeast pretty well. Then here's percent Black and percent Hispanic. So, as you know, Chicago is segregated, and so that's represented here with higher concentrations of African American residents in the west and south of Chicago, and of Hispanics in the southwest here. So next we'll load scatter plots that on the, whoops, it looks like we'll run through this again. So the scatter plots will show on the y-axis income, and on the x-axis the different racial groups, starting with income and whites, income and Blacks, and incomes and Hispanics. So here's the first scatter plot with income for percent white, which is a positive correlation. So the higher the income, the larger the percent white. And then when you do the same thing for Black and Hispanic neighborhoods, you get a negative correlation, right? So the higher the income, the lower the percent Black and Hispanic. Now, in Geoda, all of the views are linked so that as you're selecting observations in one view, they're selected in all of the other views. So we'll select the top incomes in the box plot, like here, and that selects them all over in all the other maps and in the scatter plot. So the red slope now is only the selected areas. Blue is unselected and purple is the whole city. So that initial relationship that we saw is even stronger. And there's in the actual program, you can connect can get the view of the statistical results, including the p-values, to illustrate how that works to students. Okay, so then before I turn it over to Nikhil, if your students have spatial analysis skills, there's great jobs in store for them. Here are the salaries for GIS technicians, which are pretty high. Spatial data scientists are often even higher because they have more programming skills. And these are, some of the internship and job opportunities for students with these skills that, I'd be happy to discuss in more detail during the Q&A. And so with that, let me hand it over to Nikhil.
All right, let me just share my, okay. Let me just share my screen. 1 minute. All right. Can everyone see it properly?
Yeah.
And can everyone hear me?
Yes.
Yeah.
All right. Perfect. So, hi everyone. I spent the summer using spatial data science to help create the latest version of the sampling lesson. And in this section, I'd like to walk you through what exactly went into it, what we changed from the original lesson, how we came up with the regionalization process, and more. So as you may remember, the starting point of this project was a custom map that Dash designed for one city, San Antonio. This was a really good lesson design, but it couldn't easily be updated for the new data or scaled to other cities. To do both of these things, we needed a data science solution. We created this in R, which allowed us to create maps for 100 cities that can easily be updated when new race and income data become available, or when our methods are improved upon by future generations. More concretely, here are the changes we made from the original lesson. We took the lesson from 5 to 10 samples per method per student. We made various aesthetic changes, for example, including the green space and water layers that you see on the right side, and excluding some landmarks for various reasons. Then we removed systematic random sampling, and Dash put it in his own lesson, or he will do that, I'm not sure, because we agreed that it doesn't really fit in a spatial context.
For clarity,
Then,
it's still in the lesson. It's in the day two handout. Yeah, it's in a slightly different context because
gotcha.
you wouldn't systematically randomly sample a city for incomes, but you would for like lines out of a voting booth and stuff like that. So it's in there.
Okay. All right. So we removed it from this part of the lesson, excuse me. The new lesson PDFs were automatically generated as opposed to being hand-drawn, which allowed us to generalize easily to other cities with minimal extra effort. And finally, we changed stratified and cluster random sampling to be focused around regions rather than race and location, respectively. We did this to fit better with the College Board's guidelines for how those methods are supposed to be conducted. So we had several criteria for a regionalization algorithm. Um, it had to be able to produce exactly 10 regions that are reasonably population balanced, because regardless, we are going to put 10 dots within each region, and we don't want to under or over represent any regions. Um, they need to represent demographic trends in race and income, and they need to look relatively compact, contiguous, and visually pleasing, meaning like nothing that might come to mind when you think of the word gerrymandering, for example. Um, when when aggregating on the region level, we are removing any complexity and diversity within that region and collapsing all of that region's information into a few data points. So we want to make sure that however we draw the regions, they are as similar or internally homogeneous within themselves as possible. That way, the complexity that we are cutting out is minimized. No existing algorithm fit our requirements, so we needed to develop our own solution. So first, where the data came from, we pulled our data from the US Census. When you think of the census, you probably think of the extensive rounds of data collection that happen once every 10 years. This is called the decennial, but there is another survey the census does that occurs every year called the American Community Survey, or the ACS. This provides three options for data estimates: 1 year, 3 year, and 5 year, which describes how many years of data are folded into that one ACS data set. For example, we used the 5-year estimates from 2020, which represent data from 2016 to 2020, which lowers the margins of error in the data, since this is the sample of the entire population and is not meant to be like they ask everyone for all of their data. So sorry, 1 second. Okay, so our algorithm for regionalization goes as follows, and I have created a very sophisticated animation on the right side, so feel free to try to match the steps I describe with that GIF. First, we determine each census tract's plurality race, the race that makes up the highest proportion of that tract's population. And just a note here, census tracts are geometries or delineations created by the census to more easily like conduct the census. And they're usually 1 to 8,000 people. They try to optimize it so that it's about 4,000. And you'll notice actually in the Chicago map, there's a really big census tract on the south side. That's because it has very few people in it. So anyway, then once we've labeled every tract with its plurality race, we dissolve together adjacent tracts that have the same race label, which means remove the border between them and combine them into one shape. Then we cut out small islands, which are like one or a few tracts that have been clustered together that stand out from their neighbors. And then we fold them into their nearest big clusters. So this means like in a city like Chicago, if we have one tract that is alone in that it has like one plurality race, whereas all of its neighbors have a different one, we remove that from the data set temporarily and then put it back in with whatever cluster is right next to it. Then we allocate 10 points between races based on their populations with respect to the whole city. So for example, in a city that is about 40% Latino, 30% white, 20% Black, and 10% Asian, we would allocate 4, 3, 2, and 1 points to each group respectively. Then we place these points evenly distributed within their race groups areas. And finally, we group tracts, remove all the race labels. So we completely ignore the plurality race label that we assigned before and just assign tracts to a cluster based on whichever point they are closest to. So, oh, sorry. Just want to quickly note that I put together a document that goes through all of this in more detail. The document will be linked in the chat if anyone's interested in learning more. So of course, like any algorithm trying to tackle such a complex problem, ours has its flaws. In developing this algorithm, we tried to have a certain level of consciousness of variables like race, but as you saw, that wasn't perfect. Our method ignores any race group in a tract that isn't the plurality in that given tract, which can be a big problem in cities that are, for example, plurality white in all tracts, but have a significant non-plurality population of a different race in a particular neighborhood. Our method as it stands does not consider income, which is something we wanted, but were unable to include in the time that we had. And finally, the regions our method produces aren't population balanced like we originally wanted. To reiterate, this is important because students are seeing 10 dots in each region, no matter how populous that region actually is. So that 10% sample could be very over or underrepresentative of that region's true population. The chart on the right shows the 10 regions we generated for Chicago, along with their tract counts and populations. And as you can see, the variation is pretty high. The most populous region has about 18 times the population of the least populous region. Of course, the most important part of the lesson is the 100-person population from which the students are sampling. We want this population to be roughly representative of the distribution of races and incomes within regions across the city as a whole. Here's how we generated that population. So for each region, we generate 10 evenly distributed points, and then for each point, we label it with a race and an income, where the income is roughly near that region's median income with plus some noise. And the 10 people's races reflect that region's race distribution. And I'd like to note that while this method works for the purposes of the lesson, it is incomplete. It fails to consider inter-region heterogeneity, which means differences in race and income concentrations within regions, a problem which is worsened by the enormous size of the regions. For example, in the map on the right, the region containing Chinatown, which is a highly concentrated cluster of Asian Pacific Islanders, has a high number of orange dots, which represent API citizens, but they aren't located in or localized to the subset where Chinatown is located. Instead, they're just spread out randomly throughout the region. So although limiting to 10 regions with 10 people is currently necessary based on how the lesson functions, it causes some divergences from reality within the cities. For example, because regions are so big, we must ignore but potentially significant racial clusters. For example, as I mentioned just now, Chinatown. Also, in general, region boundaries do not reflect neighborhood boundaries. This is because neighborhoods are sometimes hard to define and get the boundaries for, especially between cities and in a programmatic way. And because there are often more than 10 neighborhoods in a city, and because tracts are different from neighborhoods, but they are the best level to get consistent data. Moving forward, we are going to take another big step with this lesson, which is making it an interactive web app. The idea is that students learn the sampling process without having to do it by hand. Instead, they see it happening on the map after clicking a button. With this, we can include many more data points because students are no longer limited by how many random numbers they can generate by hand. For example, we could have it such that each census tract is a region. So if a city has 500 tracts, then we would put 500 dots within each tract for a total of 25,000 dots on the map. This means that many of the problems we outlined in previous slides will effectively go away, because as regions get more granular, they're able to preserve more and more of the underlying data's complexity. We will be building this app using a new spatial tool developed for nonprofits by Dylan Halpern at the University of Chicago's Data Science Institute. And the app is called Nectar, which is a free tool that can be used to create interactive spatial web apps. Also, I just wanted to thank you all so much for your feedback on the Google form we sent out about 2 months ago. A good portion of the areas of improvement I just mentioned were drawn from feedback from all of you. So, and we really appreciate that you're helping us make the next iteration of this lesson even better. Thank you.
Right, wonderful. Well, thank you both so much for presenting all that fantastic information. I think when we teach stats and data science generally at the high school level and the college level, it's tabular data for the most part. And that's slowly starting to expand to language data and image data as we get into more data science. But I think often spatial data is unjustifiably left behind. And it's so rich and so complex and can be so meaningful that the more we can do to bring the arts of your craft into what we do in high school, the better. And we appreciate your time and help in helping us bring that to our own students. So thank you for your time in making this stuff. I'm going to open the floor up to questions / feedback. If anyone has already used these maps in your own classroom, we'd love to hear from you. And also any questions you have for the presenters about any of the stuff we talked about, whether it's general spatial data science things, how you can get involved in bringing spatial data science to your students, what opportunities are out there for students who want to do more potentially, and also how these maps were created. So if anyone wants to be brave, come off mute, you can feel free to do so and share, or you can drop a question to the chat. We can answer it that way.
I can start.
Go for it.
I actually did this today. I was excited because, I had done San Antonio in the past. I live in outside of Los Angeles, so it was kind of like not relevant necessarily, but it was great. I was so fantastic. I was so excited to start it because I saw the maps over the summer, so I was really excited to try it. I did have some questions. I don't know if you can bring up, is it possible to bring up Los Angeles easily?
Yeah, I can do that right now.
I can, oh, Dash, you got it?
Yeah, I got it. Bring it up.
And while you're bringing that up, my question is, I love that there was a key for me to look at as far as what the dot plots should look like. And it was drawn in the median already for Los Angeles, but it wasn't written down anywhere. So I wasn't sure. I was guessing because the scale is kind of vague. So I was like, 70, so I haven't gotten there yet to talk about it, but is it written? Do you guys have the median written down somewhere?
Yeah, that's a great question.
We haven't saved the median incomes of any of these cities,
Okay.
but if we could totally like
it's fine. I was just curious. Yeah.
That's okay.
Yeah, but we have
But
it
I
actually.
can try to find it if
Yeah,
you
so
would like the
there's
number.
the blue line is the median,
Yeah.
but it's not written down anywhere. So I was just guesstimating. And then can you scroll back to the map with the not that one, the next one? Yeah. So my question was there's striped sections on the map that weren't explained. Can you clarify that?
Yeah, so the striped sections are parts of the city that are technically within the city, but for some reason had invalid data. Usually
Oh,
that means that they are empty or um, some other reason. There are a couple of striped sections in Chicago, and every time they are like parks or industrial areas, or actually the University of Chicago is one of them, because no one lives in the university itself,
right.
hopefully.
Okay.
Yeah,
So that I couldn't find that information. I'm
one
sorry.
thing I'm noticing here, this might be LAX right here, I'm guessing.
Perhaps. Maybe. I'd have to look.
But yeah, I think this is great feedback, and I did this lesson myself in San Antonio just the other day, and I was like, okay, the median was, and then I didn't have the exact numbers, so I guesstimated from where it fell here, just as you did. So that's something we definitely look at for future iterations, as well as some labels for the striped areas so people can get bearings.
Well, just so there's a legend or something. I have two more questions. Beverly, you mentioned islands within areas. Beverly Hills is a pretty big island, I think, in section 4, but it would seem to have been incorporated. So I wasn't sure. You kind of lost me in all of the talk about incorporating things. So what happened in that instance? So for example, the big island in 7 is, I see that, but there's one missing from 4. So can you talk about that?
Yeah, so the islands thing was more about parts of the city. So sorry, that was unrelated to separate cities. So about Beverly Hills, when there are situations like that, at some point along the process, we made the decision to include those areas within the city, even though they're technically separate cities. I don't remember exactly why we did that. Maybe Dash can clarify. But like early on in the process, in the code essentially just told it to, if there's any hole in the city, just fill that in and pretend that that's part of the city, even if it's not necessarily.
Got it. Okay.
Yeah, there's this trade-off between what one thinks of as meaningfully part of the city, and what is the municipal formal boundary of a city. For the context that I was thinking about in San Antonio, we have a city within our city called Alamo Heights that disincorporated from the city a while back for various reasons, but people think of it as part of San Antonio, and it adds to the richness of the activity to explore differences between life and rest, as I imagine would be the same for Beverly Hills and the rest.
Right.
And I think there's also some subtleties around, there are some twin cities, like Kansas City has a Missouri side and a Kansas side, and folks with the Kansas City map are like, why don't we have the Missouri side too, or the Kansas side? I can't remember which one right now. Same thing with like Minneapolis, St. Paul. And so we're also looking at ways to potentially, for certain cities, expand this to be metropolitan areas rather than just municipal boundaries, to get at what is the meaningful unit that people think of as the incomes in their city. And so there's a lot of edge cases here and a lot of different use cases, but we want to be able to service those.
Overall, it was really fantastic. I love it because it really brings the students, it's applicable to where they are. One last thing, I think increasing the size from 5 to 10 increase the time it takes to do all the math. So I ran into, I need more time. So I just wanted to point that out.
Yeah, that's great feedback as well. I noticed the same thing when I ran in my own classroom. And thankfully, we saved some time in it being the median rather than the means, which is helpful because they can just cross off. But also, I think maybe that's something we also look at is shortening it to be a little bit timelier with the number of samples per sample. But Jody, thank you so much for the feedback. Really appreciate it. And it's this kind of stuff that's gold for us because it helps us make this better and even more usable. Gives us stuff to do, and we really appreciate it. Thanks so much for the kind words too. Really appreciate it.
And those two things make so much sense. Adding the median income is straightforward, and then describing what the legend is also straightforward. So that we should be able to update that pretty quickly.
I think I saw some questions in the chat. Oh yes, Chicago. Oh, okay. This was related to the other question.
I know there was a question that I got via email about discrepancy between the median of the 100 households on the map and the true median as measured with the millions of households in the city by the census. Mm-hmm. I was wondering if you all might be able to discuss that really quickly, why those discrepancies exist and where does that come from?
Yeah, so the reason that we chose to exclude the true median of the city is because the way we chose the 100 dots and the way we chose drew the 10 regions was not perfect, and we knew that. And the lesson kind of exists in its own universe of 100 people per city. So including the true median of the city would not add to the value of showing like which sampling methods are more accurate, like closer to the median, because it's always going to be a couple $1,000s off from the median of the 100 people. So within the lessons universe, the median of the 100 people was shown because that's the more relevant median in this case.
It makes much. Yeah, I think there's this trade-off between pedagogical need and fidelity to reality need, and balancing those two things, you make a lot of design decisions that are hard. And I think there's a lot of instances here where it's like the median among the 100 is going to be potentially slightly off from the true median because it's 100, and balancing all the other factors that you saw in the presentation are coming in with that, and making it close might be good enough for getting still the instructive things that you want from it while giving a good enough representation of the city. But these are things that we should always be thinking about and tweaking along the way. There was some great stuff in the chat about the Desmos version of the original San Antonio one helping with the timing because it automatically generates your random samples. And I think this is potentially an advantage of the project we're exploring and making this a web app where you not only get more granularity in the data because you're not limited to 100 on a page, but you also get to click a button and sample rather than have to do rand int on the calculator and get the things and calculate the medians. There might be some pedagogical value to having students go through that process by hand, but in terms of the AP exam, it's not a lot of rand int that students have to do on the actual AP exam. And if you say sample randomly, students have to be able to describe how one would do that using random number generator, but doing it themselves, there might be questions about do students actually have to do that on a TI-84 in order to really understand what it means. So there's, again, more trade-offs to think about. Yeah, any more questions, thoughts, comments that we could potentially elucidate here?
Maybe while you're thinking about it, I have one question for you guys. Where is spatial data analyzed in high schools these days, in your classes? For instance, we've been working with some high school teachers in Chicago, and it's usually in the human geography classes where people integrate GIS. And I know that data science itself is often not yet taught as part of the regular curriculum. So I imagine spatial data science is probably even further away. And are there connections, for instance, between like stats and geography in high schools, or do teachers kind of talk to each other, or are those separate worlds?
I feel like Jody's head shake says it all.
Yeah, I this is the first time I've run into it, so it's really fantastic. I didn't realize it's a separate thing. I do have a question though. When you were talking about, because my students and my school is not in Los Angeles City, so we were talking because LA County is so huge. The city is big, but the LA County is really big. So we're in the county. And you were talking about having, and Dash, you kind of mentioned some sort of an app or something where you could do a suburb of a city that's maybe not on the map. Is that coming, or is it something possible? I'm also teaching data science, so maybe if you have code or something, I don't know. You mentioned something, so I wanted to ask about that.
Mm-hmm.
Yeah, I think we don't have an exactly defined scope yet for the new web app development. And I don't think we can make any hard and fast promises yet, but doing that project is something we're really engagedly exploring. And a hope would be that because it's on a web applet rather than on a page where you have to worry about the margins and everything, it can be a bit more expansive, while also letting students scroll in and drill down into more specific areas as they use it. And I think what's really nice about that is it also could improve the recognizability of the map, because I think a lot of students at face value don't know what a map of their own city looks like from the get-go, unless there are specific landmarks that are labeled, or they can locate their own school in it, or they can locate their own house. And having a web applet where you can go and find your address, that just is so helpful for orienting yourself to these. So these are all things that we're thinking about and hopefully can do. And I think we're also very lucky to have the Center for Spatial Data Sciences support, because it's out of my league, that's for sure. And they're the ones that are lending this great expertise to us. And we hope that as we continue working together, we can hopefully get that done and done in a way that will work. But we're still kind of exploring the possibilities there.
Yeah, this is really interesting, this comment about counties, because we've been talking about using the metro area instead of the city boundaries or the counties. There's some like 3,000 counties in the US. And so what your comment makes me think of is potentially we could explore and how far we could do full coverage for all tracts. There's, I think, 70,000 or so tracts in the US. And then letting you define the spatial extent that you want to focus on, right? I mean, right now we're pre-filtering. So we set the spatial extent, set it to 100 cities, and then you're kind of stuck with that. But in an interactive web context, if we have national coverage, we could think about and how far you could decide yourself what area you want to focus on, to then include some of the areas that are outside of the either the 100 cities or whatever, however we divvy it up. And I appreciate the answers in the chat to the geography question. It sounds like UChicago is pretty stovepiped, but it sounds like that experience generalizes.
Yeah, we can't do spatial data science in the TIE before, unfortunately. But I think we will evolve eventually once we get there. And there's a great comment here in the chat. The idea of like being able to move around the map, but also locking it so that you can have a consistent sampling frame and window.
Totally. Yeah.
I think that's something we gotta keep in mind as we keep on expanding this. One last chance. Is there any questions, thoughts that anyone wants to share with our great friends who helped make this activity and potentially are going to be making changes to keep on improving and making it better?
Thank you.
All right. Well, we're getting some thank yous in the chat, which is awesome. I'm also going to send out a speaker feedback form right now. And if you wouldn't mind just taking a second to fill this out, I'm going to put the link in the chat. I can also stop our recording here in a second. But really quickly, I just want to say thank you so much to Julia and Nikhil. And Nico might be watching from home later, for doing this work and helping us make our class more relevant and engaging for our own students. And I want to thank all the teachers on the call today. And I know that it's October 5th, and we're getting the real meat of the school year right now, and the fact that you're taking time in your evening to be a part of this, we just really appreciate it. So thank you everyone here for joining. We really appreciate it.